All right, so we're going to be looking at a question here where you have three masses that are attached by strings and pulleys that the strings are riding on, and we want to look at the acceleration of this system and the tension in the two strings. So this diagram here, we have that this is 1 kilogram, mass 2, 5 kilograms, mass 3, 3 kilograms. So however this system accelerates, all the masses are going to accelerate at the same rate because they're all attached by strings. So if mass 3 falls down at 2 meters per second squared, mass 2 must be moving to the right at that same speed, and mass 1 must be moving up because they're all connected. So we have to make a decision about which way we think this is going to move. In this case, because mass 3 is larger than mass 1, we can pretty safely assume that this whole thing is going to move to the right. Now, it's kind of hard to define one single direction for the whole system because each one of those masses is really moving in a different direction. Mass 1 will move up, mass 2 will move over to the right, and mass 3 will move down. So we'll define the positive direction for each of them to be the direction that corresponds to a general acceleration to the right, is what I'm going to refer to as sort of everything moving like this. I'm going to call that to the right. So a good step one here is to do free body diagrams for each mass. Ultimately, it's asking us to find the acceleration of the whole system and the tension in both strings, okay? And we're going to have an approach for that. But first, you want to identify all the forces that are involved, and the best way to do that is free body diagrams. So we'll look at M1, the forces involved there, force of tension. We're going to call that force of tension 1 because there's two different strings, and the tensions are not necessarily the same, so we need to label them separately. The other force we have is gravity, so we'll call that force of gravity 1. Now let's look at mass 2. Again, we have force of gravity. We'll call it force of gravity 2. This box is not accelerating up or down, so there must be a normal force that's balancing gravity, so those will be equal in magnitude. Now we have that same force of tension because it's one single string, so the tension is going to be the same on both sides. So for mass 1, that tension is pulling up, but for mass 2, it's the opposite. It's pulling backwards. But now we also have force of tension 2 caused by the weight of mass 3. Now in this case it says there is no friction between mass 2 and the surface, so we don't need to worry about that. Now mass 3 is going to be similar to mass 1. We have force of tension 2, right, because it's a separate string. And we have force of gravity 3. Okay, so now we've identified all the forces. Now these, if we're going to find the acceleration of the system, the simplest way to do it is to look at this as one unit with total mass equal to all the masses added together. You can solve for the acceleration by doing individual F-net statements for the masses and using like a system of equations. The tensions will cancel out and you can get to acceleration. But an easier way is to use what they call a system approach. So I'm going to say use a system approach to determine the acceleration. So in order to do that, we basically create a new free body diagram where instead of individual masses, we treat this thing like one big mass. So I'm going to call it mass total. So that's just going to be m1 plus m2 plus m3. And then we draw only the external forces. So what I mean by that is we're not going to include tension, because tension are forces, the tensions are forces that are just acting amongst the masses within the system. So M1 is attached to a string that's pulling on M2, but M2 is attached to the same string that's pulling back on M1. And M2 and 3 also are attached by a string that are pulling on each other. So those things have no bearing on the acceleration of the whole system. So we're just going to look at external forces, which in this case are going to be the gravity forces on either end. So because we're now treating this as a total mass, and earlier I kind of defined the acceleration as sort of just to the right in general, so I'm just going to draw it as a general sort of, this is the positive direction. So the only force that's moving in the positive direction externally is Fg3. And the only force that's pulling in the opposite direction is Fg1. So again, in the individual free body diagrams, those forces are actually pulling vertically down. But right now we're treating this as just one whole system, and our defined acceleration is just the positive direction to the right is kind of what we're calling it. So this is one way that we can kind of draw it. It's not really a physical representation of the actual direction that these things are pointing, but it will allow us to calculate the acceleration. Okay, so now we can use Newton's second law. F net equals, and in this case it's m total times a, the total mass, and F net is going to be the total force sum of the external forces acting on this system. So it's Fg3 minus Fg1. Fg3 is in the positive direction, so we express it as positive. Fg1 is backwards, so we express it as negative. Is equal to m total times a. This is then m3g minus m1g divided by the total mass is equal to the acceleration. So now we can sub all the numbers in. We have mass 3 is 3 kilograms. We know g is 9.8. Mass 1 is 1 kilogram. And total mass is 9 kilograms if we add them all up. So if we add that all up, we get that the acceleration is 2.1778. So I'm keeping some extra digits because we're going to have to use this number again. We just want to round at the very end. So meters per second squared. So that's telling us that the entire system is accelerating in that sort of to the right direction at this rate. So now we can use the individual masses to find the tensions. And this is a general approach with these questions. They often ask you to find the acceleration and then tensions in the cables. So using the system to get the acceleration, and then use that acceleration with the individual masses to get the tensions. So let's look at mass 1. So this will allow us to calculate tension 1, because tension 1 is a force that's acting on mass 1. So we're going to do the same thing. F net equals, in this case, just m1a, because we're looking at mass 1 by itself. The positive direction for this mass is up, so Ft1 will be the positive, subtract Fg1, because it's downward, equals m1 times a. But we know the acceleration now, because the acceleration of the system is the same as the acceleration for any one of the masses, because they're all attached. So that's 2.1778. So Ft1 is just equal to m1 times 2.1778 plus Fg1, which we know is equal to m1g. So if we put all those values in, we should get 11.98 newtons for the force of tension in string 1. Now we want to do the same thing to get the second force of tension. So we can pick either mass 2 or mass 3 because they both have force of tension 2 acting on them. I propose that it's easier to work with mass 3 because there's only 2 forces acting on it. So let's look at mass 3. So we've got mass 3. We're going to do the same thing. F net equals, in this case, m3a. Fg3 is acting in the positive direction. Ft2 is acting backwards in the negative direction. So that's going to be Fg3 minus Ft2 is equal to m3a. So this is m3g minus Ft2 equals m3a. Now we just need to isolate Ft2. So we can add Ft2 to both sides of the equation to essentially move it to the right. And we can subtract m3a from both sides of the equation to essentially move it to the left. So that will give us m3g minus m3a. Now we know the acceleration is 2.1778. From before, we're going to use the long answer, not the rounded answer to 2.2. And we know all the other values, so we can just plug everything in and calculate it. And we will get 22.87 newtons equals Ft2. And since the values in the question were given to 2 significant digits, we should round our final answers to 2 significant digits. So 23 newtons is Ft2. Ft1 is 12 newtons. And the acceleration is 2.2 meters per second squared. And I'm going to call that to the right. If we express A as a vector, I'm going to express that general positive direction as to the right. The tensions, we don't need to give a direction because it's asking for the tension in the string. So it's not asking for the force of tension acting on any individual mass. It's just the tension in the string. So that doesn't actually have a direction.